I've got a ukulele. In fact, I have several. But as anybody who owns ukuleles and is a nerd knows, the optimal number of ukuleles to own is n plus 1. So I need a new ukulele, but it's kind of hard to justify buying one when I already have 3 in my possession. So what am I going to do? Let's 3D print one. This isn't my first rodeo when it comes to building instruments. Here's a page from my portfolio that got me accepted into architecture school, and that is a guitar that I built in like 2001. It's a Stratocaster variant, and it was a lot of fun to play. Armed with the experience of having built that guitar and having this ukulele in hand and a caliper to take measurements, I opened up Rhinoceros 3D and got to work. But instead of copying this curvy profile, I found this picture of a woman doing yoga and I copied her curves instead. Then I found another picture of a woman's neck and I used that to make the neck of the ukulele. The next thing to figure out was the scale length and the fretboard layout, all of that. And thankfully at ukeland.co.uk, there's this ukulele fret calculator where you enter in all the variables and it spits out the spacing for all of your frets. Now, there's this nice DXF that's tantalizing. It looks like you should be able to download a file which I can then open in CAD and just use in my drawings, but it doesn't work. So I had to enter in all of these values by hand. So there are the lines that represent the frets. Next, I just copied the bridge insert from this ukulele, and then I developed this geometry here for holding the strings down at the bridge. And then came the many hours of surface modeling, which led to this final form that you're seeing here. With an environment map on it, you can see it looks chrome, but that gives you a good idea of the curves that I've drawn. It's an arch top, and my surfaces aren't perfectly tangent. You can see there's like a sharp line right there, and there's also a sharp line right here at the waist. It's not quite as bad. All in all, this would hardly be noticeable if you 3D printed it. It would look perfectly smooth. So this is that original profile that I showed you, and I was able to sort of offset it and then lower it. Then I developed this sort of curve profile, and what I can do then is get a surface like that. Then you can offset the surface so that you have 2 infinitely thin planes which can represent the inner and outer face of the wall of the guitar. There's a lot more to it than that, but you get the idea. Now, Rhino is really good for surface modeling. Other programs, not so much, but anybody who does CAD work knows that it's not a straightforward thing, and this is, I didn't keep track, but I'm guessing like 6 hours of work right here. The problem with this design is that there's really no good way to set it up so that it interfaces with the print surface on the 3D printer well. I'm going to have to use support material. There's going to be overhangs inside. It's really not designed for 3D printability. It's just designed for aesthetics. So it was time to iterate with 3D printability in mind, and that's what led me to develop this shape that you're seeing here. So this is kind of like a pineapple ukulele. You can see that it separates into 2 printable components that will both fit on the bed of my 300mm printer. That's just one glue joint to make the whole project happen, and there's 0 support material. So as far as printability goes, this is an awesome design. And looking down inside the body, we can see this bracing that I've drawn in. That's to support the face because the string tension is going to be trying to bow the face downward, and we really need to resist that deflection. Also helping with that job is the fact that I made the shell material 3.5 millimeters thick, which is quite substantial. And in fact, that's not a good thing because the thicker the shell, the less resonance. So the less volume and good tone that we're going to get out of the ukulele. But I plan to print this with PLA, so I really do need to do everything I can to give myself all of the strength. PLA suffers from really bad plastic creep. That's what you call the fact that it deforms over time when it's put under constant stress. So I either have to unstring the instrument every time I set it down, loosen the strings so that they're not putting that pressure on there, or I have to engineer it to maximize the strength in a way that you would never need to have done if you were making the ukulele out of wood. So this is a totally viable design. The only thing that's missing is the holes for the tuning pegs to go inside of it. And I haven't printed this one up. I don't think I'm going to. I was this close to doing it, but I started having other thoughts. The shape's okay. I don't mind it just because it is so printable with zero support needed, but I don't like it. I want to go back to the organic shape here. Obviously, this is so much nicer. And because I was thinking about the delicate balance between printability versus making a functional instrument, I started to realize that there's just so many variables and issues that I can't predict in CAD. So I really am going to have to iterate on this design, and that's going to take a lot of time. I'm going to waste some money in filament. And why would I do all of that when there's probably answers out there on the internet? The hive mind has already solved this problem to some extent. So I went looking on Thingiverse, MakerBot Thingiverse here, and I found several designs which taught me a lot. So this guy here has made a couple of versions. Also, this guy, Big One, has made several iterations on this same form factor. The problem with this form factor is the pegs are right there where your arm is strumming the strings, and so it's going to sort of hurt your arm. At least that's the criticism that other people who have printed this up have to say. But as far as like compactness and printability goes, this is a total winner. West Star 42 has this other design, which also is very printable, although it does break apart into two pieces, which you have to glue together. So pretty decent, but not ideal. These two projects were the best that I found, and they didn't inform my design process at all. They didn't teach me anything that I could use to make this design more viable. Maybe tweak this so that it's more printable. I mean, I could chop it in half, but I still can't print these shoulders because there's going to be support material needed up here. So I expanded my search to include guitars that are 3D printed, and I came upon this video by Jeff Kerr. I'll put a link to it in the description. Man, Jeff deserves so many more subscribers than the 2,000 subscribers that he has. He's been at this since 2016. Wow, that was 6 years ago that he came up with this. So I'm only now catching up, but just so much intelligence built into this guitar design. He has a very thin skin as the surface of the guitar, so it will resonate really well. Think of a paper speaker cone, very thin membrane to vibrate, moves the air very efficiently. But to add stiffness to such a thin membrane, he put these triangular ribs. Then he's got these giant X-brace ribs made out of aluminum to really add stiffness and to fight the creep, the plastic creep that's going to happen from the strings over time. So just so much intelligence. Jeff Kerr is clearly a clever engineer. He looks like he's a retired engineer, and these are just sort of his hobby projects. So I am just immensely impressed, and I'm going to take this idea and run with it in my next design. So it's time for me to put my headphones on, get into a state of flow, and start drawing. And that's what this is. 3 hours of drawing in CAD nonstop, condensed down into just under a minute. And there's a couple of interesting things that you can learn from watching the time lapse. First of all, those moments where the screen is frozen, that's not where I walked away from the keyboard. That's where I'm just sitting here staring at the design and trying to figure out what to do next as far as the design process goes, not for the CAD program. But when I'm actually productively working in CAD, it's really interesting how the major form comes together so quickly. Like they say the last 10% takes 80% of the time, and that's the way it goes. You get the 90% of the form done in just like lickety split, and stitching together those last few surfaces to get the neck of the ukulele here in this case was the hard part. But it came together pretty well. I had to redraw the neck a little bit, and as you see here, now that I've turned it chrome with the environment map on, it did have kind of a funny bump. It was perfectly tangent everywhere though. Really, I did really good with the tangencies, but I had to get rid of that bump, and that was this design. So this added an extra hour to come up with the better geometry that you're seeing here. But all in all, I am really happy with the way this external shell of the ukulele turned out. This just fills me with excitement, and I can't wait to have this thing in my hands. So that was 4 hours of work that you just saw me do, and the bulk of that was just coming up with the surfacing for the body of the ukulele. I'd already come up with the fretboard and the neck to a large extent, so just some rework there. But then I've spent at least another 8 hours to come up with these 3 iterations that you're seeing on the screen now. And I mean, I've been working on this in CAD here for days. The final version right down here, I think this is fantastic. You can see there's no lip. So that sound's going to be able to come off of the strings. The front face of the ukulele here will act like a drum head, and it will transmit the sound which will because the shell is curved. So the sound waves will propagate down along the curves and come right out of this hole with no lip. So it'll be like a loudspeaker. I think we're going to get really great sound resonating out of this 3D printed body. And you can see I've got the peg holes in the headstock up here, and I've also split the ukulele into its constituent parts for printing. So you can see I've got a fretboard here, I've got the two pieces of the neck, I've got the bridge. Now there's a good reason I had to cut the neck in half down the center and cut the fretboard off of it, and it's because of structural considerations once the thing is built. Remember, those strings are providing tension. They're wanting to bend the ukulele like this. So I need to fight against those forces with good grain structure in the print, which means I need to orient the layers in a certain way to have continuous loops where it maximizes strength to fight against that bend. And so chopping it in half is the best way to do that. It requires no support material, and I'll easily be able to glue those two halves back together and then glue the fretboard on top, which also the fretboard should be printed in this orientation for the best, smoothest, most usable fretboard that doesn't require any sanding. So all in all, this is going to be reasonably printable, not nearly as print friendly as the design which I already talked about, the two pieces with zero support, but the whole point of this design was printability. It was no other considerations. All other considerations were secondary to printability. I've got my large format Mingda D4 Pro heavily modified with a Duet 3D control board and an e-stop switch, and this was the custom printer that I built for making large format prints, and it works really well. Now, Mingda doesn't sell this model anymore. I'll put a link in the description to the updated version of this printer. I really like Mingda, so if you want to do projects like this, it's a fantastic large format printer for you to get. But let's talk about the print. It's got about 4 more hours to go. The wall is basically just going to be a lot taller, but it'll look just like it looks here. And you can see I've got this triangular support structure going on without a top layer. So that'll allow the front face of the ukulele to resonate, to vibrate like that, and transmit sound through the triangles there into the cavity that is the ukulele body. The way I accomplished that printed geometry was by using a couple of tricks in the slicer software. Now, I went back to Simplify 3D, which is an antiquated program that I'm not using as my primary slicer these days, but I knew that I could accomplish what I wanted to do using this program, so I used it just for this geometry right here. Top solid layers, 0. So it doesn't have a top surface that it's printing, and yet it has an infill of 8%, which is giving you the gaps in between the triangles. So there's the triangular infill of 8%. But when it was time to slice the backing plate for the body, I jumped over to Super Slicer here because of the paintable supports. Now you can see, whoops, the red line's there where I'm blocking supports being built, and the blue or purple surfaces are where support is going to happen. Now in the slice preview for this geometry, we can see that I've minimized supports by putting the geometry up at 45 degrees. So it's mostly just printing with the 45-degree overhangs, which we all know FDM printers can handle. And then just this front edge here gets a little bit of support just so that it's not doing a whole lot of bridging. And all in all, I think this is going to yield a pretty good result. I am a little bit worried about the final aesthetic with the layer lines, how they don't match up because this is at an angle and the other geometry was flat on the bed. But hey, that's a problem we'll solve in the real world after this gets printed. The back plate is done printing, so let's just pull that off the bed here. As you guys saw, these two prints were printed in different orientations. This one was printed like that, and this one was printed at a 45-degree angle. And even though this is a PLA material, I'm still getting problems with shrinkage. You can see the layer separation there. And if shrinkage is what's happening, that would tend to straighten the curves out, so they wouldn't be quite as pronounced as they were supposed to be from the CAD drawing. And that's exactly what I'm seeing when I try to get good fitment to happen. Basically, the curves from the body are not matching up with the curves from the backing plate. They match up okay when you're here. So if I'm going to hold this one, that's a nice smooth seam. And then you look over here and I've got a good 1/8 of an inch almost of stick out. So I'm going to have to flex that in as I glue it. I've got the back plate attached to the main body, and you can hear that the thing has a nice sort of resonance to it. So I think this is going to work, you guys. I'm pretty excited. The cracks that you're seeing are actually the glue joints, and I accomplished that using a soldering iron. So I just dragged the tip of the soldering iron in the crack. And yeah, I did sort of tap this on my palm to sort of test for strength, and that broke it along the layer lines here. That's the thickness of the triangulated support structure underneath the front plate here. And so yeah, it cracked along there, along the whole instrument. So I had to glue that back together. And then of course there's the joint where the back plate comes in, and then you can see some of these separations, the layer lines separated when the shrinkage occurred during printing. So I've sort of enlarged those, and what it does is it not only glues them together by pushing some of that molten plastic back into the crack, it also creates a nice chasm, a nice valley to fill with 3D printer pen. So this is just a whole lot of handwork that I wasn't planning on doing, but once I've filled all these cracks with 3D printer pen, they will be very strong, stronger than the base 3D print, and then I'm just going to have to sand and carve away at this till it's nice and smooth, and you don't see any of these artifacts. It's going to look quite nice. You also won't see any of the layer lines anymore, so all in all, it will be a nicer product, but it's going to be a lot of labor that I wasn't planning on doing. So once again, you're looking at 4 hours condensed down into just under 1 minute worth of drawing, and what I'm doing is something not for the faint of heart. I'm having to generate a worm gear from a helical gear and a rack, like a rack and pinion, and that worked out quite well, and now I just got to get it to fit. So I'm sure that there are gear generation plugins for other CAD platforms that can do an automatic worm gear, but the gear generator for Rhino doesn't give you that functionality, so I had to do it kind of by hand. But yeah, so these are the machines that I'm making, and then just a little bit of polishing up work so that the two halves of the neck will join together nicely, and so that the machines, the tuning machines, can kind of fit together and fit onto the stock really cleanly. With the neck and stock geometry finalized, I split it in half and laid it out ready for printing. Then I added a couple of, or actually 3 boxes here, these 3 strange shapes. And those are modifier boxes, which I was able to import into Super Slicer so that I could change where the support material, or I should say the infill material inside the hollow cavity of the neck would appear. I don't need support material everywhere, and because this is a rather large print, I would like to save on material and be as miserly as I can, just to save on time and to save on material. So that's what I ended up with. Here's the preview. You can see there's just support material there near the top, and then it's just hollow after that, and it's time to get this onto the printer. So on this print, the headstock is workable. I got a little bit of elephant's footing, so I'm going to have to sand that until it's nice and smooth. But there was some weirdness happening down here. Part cooling was on, and yet you can see the support material was unable to bridge. So, I mean, the support material bridged, but then the top layer fell through the support material, even though part cooling was on. So this is kind of strange behavior, and I don't fully understand what's going on there. I don't use Super Slicer a lot, so some setting was set wrong, and that's why that happened. I'll have to figure that out. Got these things that I printed, and they are little dominoes. It's a bit of a press fit, but they go into the slots here, and that's how I'm going to book match the 2 halves of the neck. A little something like this. I've been filling up the cracks, sanding them, carving them with a knife, you know, all the handwork to get to this point, and it doesn't look great. It's like I'm gonna have to sand it and fill it with some high build body primer and then paint it if I really want a nice surface there. Now it's time to seat the neck. Using some cyanoacrylate gel, superglue gel, to glue the fretboard to the neck here. I've got the tuning machine 3D printed here, and the middle C string strung up. This is just to test. Do, re, mi, fa, sol, la, ti, do. The volume and tone coming out of these 2 instruments. This one's louder. looks like crisper. I like it. All right, it's all strung up and tuned up and sounding better than it has any right to sound, but it's time to call it quits because the whole time that I've been working on this ukulele, I've been struggling against the problem with layer lines. And we all know layer adhesion and the strength in the Z direction is the Achilles heel of FDM 3D printing. And this project really pushed that to the edges, to the extremes. I maybe could have used a better PLA filament, like some name brand filament that had really good layer adhesion even as a PLA, but I didn't. I used what I had, and even with a name brand, I still would be struggling with that. You guys saw me having to re-glue together the layers in this direction and fill the cracks from the layer separation during shrinkage on the back plate, but the latest casualty is the cracks here in the headstock being caused by the tension in the strings sort of blowing it apart up here. So everything about this ukulele struggles with layer adhesion. Let's just play this chord here and then listen. You hear it bending up like a whammy bar? That's me bringing the ukulele back into shape the way that it was designed to be. So the strings are effectively flexing the neck up and giving me what's called a high action. And that means I need to press the strings down a long distance, which as you're stretching them down to get to the fretboard, it creates more tension on the strings, which pulls the string sharp, and now your instrument sounds like crap. So you really need that action to be the right height, but the problem with the action being the right height, normally you just shave down the bridge here to bring the action down, and the problem here is that I'm getting fret buzzing even with this really high action. So yes, every string is getting fret buzzing, and it's only going to be worse when I have lowered action. So this fretboard was a total failure, and you can see I didn't really talk about it much, but I've tried this like stair-step angled fretboard design. I'd seen this on an electric guitar years ago, and maybe it would have worked in this case if I had made the frets taller. I matched the normal fret height of 0.75 millimeters from normal ukuleles, and if I had made that like 1.25 millimeters tall, I think it wouldn't be having the same problems. So basically, it's almost behaving like a fretless fretboard. If I hold the note, like let's just hold this one here, you're getting buzz, and that buzz is coming from the fret itself. You can see if I put my thumb right there on the fret, we get a nice clean tone. I just sort of threw a bunch of things in there without knowing how they were going to perform. This was largely an experiment, and hey, as experiments go, it was quite successful. That fret buzz is pretty bad though. Now, one thing I didn't think about until I had the thing in my hand is that this ukulele has absolutely no metal. Nothing, like not even a speck of metal anywhere on it, which means that because it's made out of all plastic, it's a waterproof ukulele. Bet you didn't know that I have a secret power. I can play the ukulele in the shower. And I've never seen that before, and it was only made possible because I've got these 3D printed tuners. And I made those on the resin printer because I needed the isotropic XYZ strength to all be equal, and also I needed the fine resolution on the gear teeth so that they would mesh really well together. And yeah, as you saw when I was tuning it up there in the beginning, they function fantastically. So I'm really happy with those tuners. They are a little sticky, a little ka-clunk. Maybe just some more lubrication. That's graphite lubricant that's turned it black, and also that's sort of contaminated the white. But that is totally workable as far as I'm concerned. And what's not workable, layer lines and potential creep. I haven't even mentioned this yet, but over time, when PLA is put under pressure, it deforms. If you've ever had like the infamous place where most people have become aware of this is the headphone clamp. So lots of people printed a headphone clamp for their desk where it sort of clamps on and you got a little hook for your headphones. And over time you notice that it gets looser, and so you tighten it down again and it gets looser. And then you go back and you take it off and you go, what's going on? And your clamp, instead of looking like this, looks like that. It's spread apart. And that's just called plastic creep. And PLA is not a great material for plastic creep. Now I'm told that you can put additives like carbon fiber or such things into PLA or other plastics to help with the creep, but it's not like it's 100% effective. It helps, but it doesn't solve the issue. So I think that over time, this neck is just going to keep on moving. It's just going to keep on coming up, and that means that it really does need a truss rod inside of there to allow you to mechanically pull it back down. You can tighten down, there'll be like a nut here or up there that you can tighten down, and it pulls it, mechanically just pulls it down. Other people that I've seen online using a piece of carbon fiber rod or some other thing that they've embedded in the neck to solve this problem. But yeah, that's, I think, going to be the Achilles heel. And I was always expecting that. In fact, that's why I made this ukulele the way that I did. I'm going to keep it strung up for a couple of days, couple of weeks, whatever, just to see if it does deform over time. But one thing that I don't think is going to deform at all, that's that front plate. And the reason it sounds so good is because it is just such a thin membrane, and those structural ribs, the triangulated ribs, are what's keeping it rigid. And oh man, it hasn't deflected like at all. You would be able to see it in the reflection off of the flat surface, and that is just rock steady. So tremendous win there, very surprised. All in all, really successful project. I wasn't expecting an instrument that was going to last, and I was going to be happy if it even played, and it does. So, yeah, so it's a thing. Thanks for watching. These are my Patreon supporters. They keep me making videos. I love you guys. Thank you so much. See you in the next one. Bye.